I'm going to talk about some endpoint of stars which are revealed by supernovae. So let's start. Yes. So as I'm showing many times, this figure shows the mass loss rates of massive stars. So at the so this is luminosity and mass loss rate, and of course mass loss rate can also differ based depending on the temperature. And the main sequence temperature is relatively high, and the main sequence mass loss rates are around there. So at the highest end, let's say it goes to 10 to the minus 5 solar mass per year or so. And then as stars cools down, they go to red supergiants, and the cooler stars tend to have higher mass loss rates. And so there's some uncertainty in the red supergiant mass loss rates, but they come around here and they go up to around 10 to the minus 4 solar mass per year. And yeah, wallflower stars are also around there, and they basically mass loss rates goes up to like around 10 to the minus 4 solar mass per year. There's some exceptions, but that's the standard mass loss rates you get by observing the stars around us. So these, of course, supernova progenitors are losing having these mass loss rates, and the stars are exploding inside the circumstellar matter, which are created by these mass loss from these progenitors. And so this is typical one example of mass loss. Change of mass loss rates as a function of time of these stars. So this is one example of 30 solar mass stars, 35 solar mass. During main sequence, it's like between 10 to the minus 7 solar mass per year and 10 to the minus 6 solar mass per year, and it gets a bit slightly higher. And then as the star expands, so at this phase, it stops burning hydrogen and it goes to red supergiant, and that's why mass loss rate increases and it gets close to 10 to the minus 4 solar mass per year. And then this star loses all the hydrogen-rich envelope, and so this is red supergiant phase. But at some point, it loses all the hydrogen, and then it goes to wallflower stars. So that reduces the mass loss rate, and then at the end of the evolution, the mass loss rate is expected to be, let's say, order of 10 to the minus 5 solar mass per year. So the star ends, it explodes there. So, and based on this, based on this, based on this mass loss history predicted by the stellar evolution theory, we can construct the density structure of the expected density structure surrounding these supernova progenitors, and this is one example at the time of explosion. So this is density. It doesn't have unit, but this is gram per cc, I think. This is the density structure. So this looks like this, and supernova explodes inside this structure, and so supernova ejecta basically runs into this circumstellar matter. What's the effect we expect from such circumstellar matter? So basically, these masses are quite small, especially just near the progenitor where we observe as supernovae. So we don't. So if the supernova occurs in this kind of usual circumstellar matter expected from normal stellar evolution theory, which dies, the circumstellar matter mass loss rate was 10 to the minus 5 solar mass per year or so. You don't expect the supernova properties are not expected to be much affected by this circumstellar matter, because supernova ejecta is, let's say, at least several solar masses. This circumstellar matter just near the progenitor is very like much smaller than this ejector mass. So you don't expect to have much effect in the supernova property. But so what we can see is that at the forward shock, some electrons there can be accelerated this forward shock. So there can be a synchrotron emission from this interaction between the forward shock and the circumstellar matter. So in radio, in supernovae, I mean, from the main part of the supernovae, there won't be radio emission because the brightness, the temperature is much higher. But in radio, if we observe supernovae, we can see this synchrotron emission coming from this accelerated electron at the forward shock. And this is one example of observed radio light curve at 8.4 gigahertz. And this is the dots observed luminosity, and this is a synchrotron self-absorption model. This radio light curve can be easily naturally described by this interaction electron acceleration at the forward shock. And you can easily estimate how the velocity and density of this forward shock by using some simple analytic formula, and you can easily derive this behavior. So that's kind of standard supernovae, and that's what we expect from the stellar evolution theory as well. But recently we start to see very weird supernovae, and this was also introduced before, and this is type 2, something called type 2N supernovae. And N is coming from narrow, and this blue line is one example of type 2N supernova spectrum, and this red spectra is typical type 2 supernova spectra. And of course, supernova has huge explosion energy, so supernovae have these broad lines. But in this type 2N supernovae, we see very narrow lines. And in some cases, when you can take a very high resolution spectra, then you get something like this from type 2N supernova. And what we see is this very narrow P Cygni component can be observed sometimes. And this P Cygni profile indicates there should be outflow of 100 km per second or so. And this is on top of this relatively broad component. And supernovae should have thousands of kilometers per second. So this 100 km per second ejecta is, I mean, something must be moving in 100 km per second, but that's too slow to be originating from the supernova itself. So what's happening? So what we think is there should be dense circumstellar matter surrounding this supernova ejector, and this dense circumstellar matter, unshocked circumstellar matter, this is moving outwards with, let's say, 100 km per second. And then the supernova explodes inside this dense circumstellar matter, and then this ejector collides to this dense circumstellar matter, and there will be shock which can illuminate this dense circumstellar matter, and that is causing this narrow P Cygni profile. So this so this type 2N supernovae indicates that there should be some dense circumstellar matter surrounding this supernova ejector, and this dense circumstellar matter should be created by the progenitor before the explosion. So this kind of type 2N supernovae, it's not very common, but it's not rare either. So about, let's say, about 10% of core collapse supernovae are now known to be type 2N supernovae. And so this is not usual, but it's not like extremely rare event. Some kind of progenitor should be losing a lot of mass before the explosion. So the question is what is the mass loss rate, or how much mass should be is surrounding these type 2n supernova progenitors, and then what's the mass loss rate of the progenitors to make this kind of type 2n supernovae. So to answer this question, we can make some simple models. This way of so these type 2n supernovae, we clearly see the signature of interaction between circumstellar matter and supernova ejecta, and they are probably illuminated by the interaction between supernova ejecta and circumstellar matter. This luminosity source was discussed in the Masaomi's lectures. So there will be supernova ejecta from inside, and then there should be dense circumstellar matter, and this collision between this supernova ejecta and circumstellar matter is making this type 2n supernova bright. So we assume some simple density structure as supernova, and then we assume some power law as circumstellar matter. And we assume this power law for circumstellar matter structure. And that's if we do very simple conservation of mass, then what you expect from the steady wind is that this power, so we expect simple power law density structure from constant mass loss rate and constant wind velocity. So this, if this S, I wrote this here S, but if this is coming from steady mass loss, then this should be just 2. And if we can get this density structure somehow from the supernova observation, then assuming some wind velocity, of course, we can also get some idea of mass loss rate causing this supernova. And wind velocity is, let's say, typically of the order of the escape velocity of the supernova progenitor. So we can have some rough idea of wind velocity, and then once we get this density, then we can get the mass loss rate from the if we can get this circumstellar matter density. So if there's a shock wave going into the circumstellar matter, then there will be a thin shell there, because there will be radiative cooling causing making this supernova bright. So there will be very thin shock, which can be just assumed to be just a kind of thin shell or thin shock. And if we assume there will be just one thin shock there, then the motion of this this shock can be easily described by taking into account of conservation of momentum or equation of motion. So the mass of the shock that in this shock can be m shock, and then there will be velocity, and this evolution should be described by the so this is the so this shock velocity minus this ejecta velocity. So this part is momentum coming from the supernova ejecta itself. So this component is basically describing how the supernova pushes this shock. And then, of course, there's a dense circumstellar matter which basically tries to decelerate this shock. So this component is this shock minus wind velocity and times this density. So this is a simple model to describe the movement of this shock between the circumstellar matter and supernova ejecta. And actually, I said this. And actually, if you put these numbers, you can solve this equation analytically, and you get this simple formula, power law formula. So shock wave evolution should be this power law. So S was this circumstellar matter density, and which should be 2 if this is from steady mass loss. And N describes the outer density slope of the supernova ejecta. And then assuming some kinetic energy of this shock wave is converted to radiation, and of course this epsilon is kind of uncertain, but let's say if 10% of this shock kinetic energy is converted to radiation, so we can describe this luminosity of supernova in this way. So some kinetic energy should be going to radiation, and then we can just plug in this new our description of the shock, which we can obtain by solving this equation. Then what we get is basically luminosity of this supernova powered by the interaction should be described by T3 alpha, and alpha can be just obtained in this way. So that's very simple model for the interacting supernovae. So we got this formula and this alpha power here. So basically interaction powered supernovae should be some sort of power law. The luminosity should evolve in power law, and the power can be described in this way. And this is several different power for several different n as a function of s. And if the mass loss is steady, then we should look here. And this n was the outer density structure of the supernova ejector, and we can get some idea from the numerical simulation of explosion. And let's say 10 and 9-ish is obtained for Wolf-Rayet star, so compact star explosion. And red supergiant explosion is we typically get like n equal -12. So that's the difference you see here. So since we now got this this formula, we can apply this theory to the actual observations, and we can fit this power law formula to actual observation. And this is one example. So these red dots are one well observed type 2 n supernova, and this is luminosity evolution for like 200 days or so. And when we fit this light curve with simple power law, we get this value. So as you can see, you can describe this evolution by power law as expected from the model. And assuming if we assume like a Wolf-Rayet star explosion, then that means we should see like n equal 10, and we got like minus 0.56 and 0.56 or so. So we can see somewhere there. And of course, depending on which one you choose, but it tends to be slightly higher than s equal 2, which you expect from steady mass loss. So we see maybe the mass loss was not, it's consistent with steady, but maybe slightly different from the steady mass loss. So that's let's say this model is this is the fit. And to confirm if our numerical model is doing well or not, we also did some numerical simulation of radiation hydrodynamics. So based on the analytic model, we can get what kind of density structure is expected from this in this type 2n supernova, and we can put exactly the same structure in a numerical radiation hydro code, and then see what happens. And then this orange line is basically the result of the radiation hydrodynamics simulation. So we can also see this simple analytic model is doing a good job. Yes?
Go back. 2 slides back.
More?
So
yeah.
we when you compare the numerical simulation, what's epsilon?
So epsilon can be changed in the numerical simulation as well.
Oh, yeah. So what exactly?
So in this case, like 0.1 was good. But of course, in the numerical simulation as well, we have some parameter to adjust this efficiency. So it's hard to tell which, I mean, so we basically adjusted this epsilon to have a good match. Yes, it's around 0.1. So by doing this, we can get the density structure of around the circumstantial matter. So basically, I didn't show this A or L1, and this has a very complicated way of, complicated formula. But then we can get the density structure by applying this kind of model, and then based on this this model, we can get some mass loss rates of the progenitor. So these are all obtained by fitting this kind of model for type 2n supernovae. By using the numerical analytic model I introduced you, we can get the mass loss history of the progenitor, and these are results of mass loss estimates. So this is before the explosion. So at this time, supernova has exploded, and then because we have the radius as the supernova ejector goes farther away, that means we are tracing the mass loss happened longer before the explosion. So we can get some also get the idea of the mass loss history of the progenitor before the explosion. So we can see several things. One thing is as expected. So this the mass loss rates we get from type 2n supernovae typically higher than 10 to the minus 3 solar mass per year. And as we saw, these normal stars we observe has mass loss rates up to 10 to the minus 4 solar mass per year. So these type 2n supernova progenitors are somehow having large mass loss rate just before the explosion. And also these type 2n supernovae are bright for a long time, and in these cases we can trace up to the point of the light curve observation, but basically these should be kind of extended because they are type 2n supernovae are bright for many years. So these are probably extended. So this mass loss rate increase should be like lasted for more than 100 years before the explosion. And not only mass loss rate is high, in some cases you see some difference, change in the mass loss rate as you get closer to the explosion. Of course, this is very subtle thing, and basically they are of course consistent with the steady mass loss, but in some cases we see mass loss rate may be increasing as you get closer to the explosion, and of course some cases it doesn't, but there seems to be some correlation between the time of explosion and the mass loss rate. But this is not fully clear. But in any case, this mass loss rate must be increasing more than 100 years before the explosion compared to the standard stars we see in the in our nearby universe. Yes.
Maybe I'm missing, but how the mass loss rate history is determined?
So by fitting this light curve, we get these constants. And then I didn't show how this L1 is described, but you can. This is a function of many different like density and ejecta mass and so on. And the ejecta mass and the velocity is degenerated, but assuming some ejecta mass, we can break the degeneracy. And by putting these constants to the actual fitted value, then you can get the density structure. So you can get this D basically. Once you get D, then that can be translated into the mass loss rate, assuming some wind velocity. And here I assume 100 km per second. So basically what we are doing is to get this density structure. Once we get the density structure, we can interpret this as a mass loss history. And so mostly they are like 10 to the minus 3 solar mass per year or slightly higher. But we can have more extreme case. And if this circumstellar matter is extremely dense, then this dense circumstellar matter will be opaque, and the photons released at this shock will diffuse in this circumstellar matter. The previous model this kind of model is assuming the radiation from the shock will be not affected by this circumstellar matter and just goes away, and that's why we assume this circumstellar the luminosity will be directly converted to this actual observation. But if this circumstellar matter is opaque, then the photons released at the shock will be diffused, and it takes time for the photons to reach the observer. I mean, to be emitted from this system. So the model I introduced cannot be directly applied to this kind of extreme system. And then what we can do is use the radiation hydrodynamics models, and this is one example of supernova called 2006 GY, and this is a type 2N supernova with extremely bright luminosity, and in this case we needed to have really dense circumstellar matter to explain this huge luminosity. And this dense circumstellar matter is opaque, and we need to do it in a numerical way. And we really need extremely large circumstellar matter, and then this mass loss rate of the progenitor should have been like close to even 1 solar mass per year or so. So this mass loss rate should be extremely high. And so 1 solar mass per year also, so this extreme case, so in normal type 2N supernova, it's already 10 to the minus 3 solar mass per year, and it's already quite high. But in some cases, we see like reaching 1 solar mass per year or so. And those we don't know exactly how we can have such high mass loss rate. And we know one example of the star having such high mass loss rate, which is this star Eta Carina. And Eta Carina had a mass loss rate close to 1 solar mass per year, or even higher, for 10 years during during the period which is called Great Eruption. So this Eta Carina got bright from like 1845 or around so, and it got bright for about 10 years. And now we know this structure we see around this Eta Carina was created during this Great Eruption. So it has like 10 solar mass or even more in this shell, and then it was bright for 10 years, so the mass loss rate should have been like 1 solar mass per year or even more. But So we know this kind of star having this kind of huge mass loss rate, but as this circumstellar matter expands, the density of this circumstellar matter gets lower and lower, and that for circumstellar matter to affect the supernova property, this circumstellar matter needs to be located just near the progenitor. So it shouldn't be. So as the time goes, it goes away and away, and it gets less dense and less dense. So the effect for supernova will be much less. So Eta Carina didn't explode at this time. So somehow some supernovae are exploding just after having this kind of eruptive mass loss, and then it should immediately explode. And we don't know how these two phenomena are connected. So those are type 2n supernovae, which has kind of clear signature of circumstellar matter, and we know these progenitors are having extremely high mass loss rates. So as I said, this is for like about 10% of quark supernovae doing this kind of mass loss, and so it's kind of rare. I mean, 10% is not very extremely rare, but still it's a small fraction of all the quark supernova progenitors. But recently, we are starting to realize maybe this kind of mass loss should be operating in many, even in ordinary type 2 supernova. So this is one example of supernova light curve models, and this is type 2p supernova, and these numerical models are explaining this light curve evolution relatively well. And this is explosion of 15 solar mass red supergiant and explaining these light curve well. But one issue which has been realized in the last 5 years or so is in this early time. So late phase, the model is relatively doing well. The early phase, its model is actually rising slower than what observed. So this is kind of a zoom up of another example, and so this supernova was observed very shortly after the explosion, and then has a rise, and then became a type 2 supernova. So there's a plateau. And if we do numerical modeling, usually if we explore like normal type 2 red supergiant progenitor for type 2p supernovae, the rise time will be much longer than 20 days or so. Of course, depending on the bands, but let's say R band, G band, it takes more than 10 days. But it has been realized around 5 years ago that I'm showing one example, but usually type 2 supernovae rise in 10 days or less, and most of the theoretical model predicts the rise time for type 2 supernova should be much longer than that. So as was explained before, this first rise is basically coming from the adiabatic cooling time scale of this huge progenitor, and red supergiant radius is 500 days. So if the red supergiant radius is more than 100 solar radius, then we cannot avoid having the rise time more than 10 days or so. So the big question was why there's this kind of discrepancy. And the big advantage, or a big hint to solve this question was provided by this particular supernova. And what was great about this supernova was they discovered this supernova about 3 hours after the explosion. So there's non-detection, and non-detection there, and they found here, and this is the light curve in hours after the explosion. So they discovered this supernova there, and what was great was they happened to have some observer at the Keck telescope, so they could take the spectra immediately after the discovery. So they found this supernova 3 hours after the explosion, and then they took the first spectra at 6 hours after the explosion. So they could take very early spectrum. So the spectra they got looks like this, and this was 6 hours after the explosion, and 7, 9, 10. And what they found is that this spectra is really narrow. So they found the supernova just after the explosion looked like type 2n supernovae with narrow lines. Then, of course, they kept observing, and these narrow components got weaker and weaker. And after like 5 days after the explosion also, it became just a normal type 2p supernova. So this was just after the explosion when they observed within a few days after the explosion, this supernova looked like type 2n. But then, after a while, it became just type 2p, normal supernova spectrum. And this is the earliest spectra they got, and they modeled this spectra and estimated the density required to explain these narrow lines and so on. And this was the density structure they estimated. So this is radius, and this is the density. And from the early spectra, they found the density should be around there. And this is, as we saw, this density is something required for type 2n supernovae. You can see these several lines showing the mass loss rate. So this yellow line corresponds to 10 to the minus 3 solar mass per year. So this line is basically in the regime of type 2n supernovae. And so this was at first when they first observed 6 hours after the explosion, the density around this supernova was like those in type 2n supernova. But then after a while, they found this narrow component just disappear, and this supernova became just a typical normal type 2 supernova. So that means the density, this high density didn't continue for a long time. So at some moment, this density became very low, and went down to the regime of normal normal supernovae, which should be like 10 to the minus 5 or 10 to the minus 6 solar mass per year. So this was normal type 2 supernovae if we were observing this after like 5 days after the explosion. But since we observed early enough, we found that transition from type 2n supernova to normal type 2p supernova. So this indicates there should be some dense circumstellar matter should be sitting just near the progenitor, and not much. This dense circumstellar matter should not be extended much. So that was about the spectra, but let's see how this kind of dense circumstellar matter sitting just above the progenitor will affect the light curve. So the big question we had before is this rise time is much longer than what we observe. So if there's no circumstellar matter, then this dashed line is the model I showed previously, no circumstellar matter. Then if we put, let's say, 10 to the minus 5 solar mass per year up to some radius, and that's something you expect from this low mass loss rate is something you expect from the standard stellar evolution theory. And the light curve will look like this solid line. So 10 to the minus 5 solar mass per year, it's quite low, and you don't see much difference. But as you increase, so 10 to the minus 5, it was somewhere there. But as you increase, let's say if it gets close to 10 to the minus 3 solar mass per year, then you start to see clear difference. So this early light curve is strongly affected by this dense circumstellar matter, because as we are seeing, if there's dense circumstellar matter, this shock will be radiative, and you start to have extra energy source to make this supernova bright. So if there's no dense circumstellar matter, this early emission is basically coming from adiabatic cooling of the envelope. But if there's a dense circumstellar matter, like expected from this spectral modeling, you start to have a huge deceleration from this dense circumstellar matter. You start to have this brightening at just after the explosion of these red supergiants. And in this model, I just assume this constant mass loss rate and wind velocity. But as we get close to the progenitor, so this is the radius and this is the density. And from the spectral modeling, we got the density should be density at this radius should be around there. So that's obtained from the spectral modeling. And as we get close to this progenitor, so this basically we obtain the constraint for density of circumstellar matter really near the progenitor. And this wind is not, the terminal wind velocity is like around 10 km per second for the case of red supergiant, which corresponds to the escape velocity of this red supergiant. But of course, at first, wind is not the material at the surface of the red supergiant doesn't have the velocity, so it's basically zero here. But from the surface, it gets accelerated to the terminal velocity of around 10 km per second. So the velocity should be close to zero here, and then it should reach to the final velocity at the far away. So as we get close to this progenitor radius, we need to start to think about how this wind will be accelerated, and that can change the density structure of the circumstellar matter. So we were assuming just the wind is constant in the case of, let's say, type 2n supernova model, because we were just thinking about much farther away than progenitor. But in this case, we are just seeing just above the progenitor, and this wind acceleration itself gets very important component to think. So we not only mass loss rate, but we also need to change this wind velocity. And of course, if the velocity gets lower, then you get higher density, and that's why you see higher density near the progenitor if we start to think about this wind acceleration. And this way of describing how the wind is accelerated is kind of simplified way. There's a parameter beta, and that basically describes how fast wind will be accelerated. So beta, if the beta is 1, which is this green line, the wind will be accelerated to the final velocity very quickly. But if the beta is 5, for example, which corresponds to this violet line, and the wind acceleration will be slow. So it takes time for this wind to reach the final velocity. So if we take this effect also into account, we can get this kind of light curve. So this dotted dashed line was those without circumstellar matter, but now we have 10 to the minus 3 solar mass per year with some wind acceleration parameter, and we start to see those light curves matching relatively well. So this was one particular case of the 2013 FS, which we had the spectra to constrain the actual density around the supernova. So in this particular supernova, we could constrain both from the spectra and the light curve what kind of dense circumstellar matter are required to explain this property found just after the explosion. And to explain this rapid rise in the light curve, it was natural to have this kind of dense circumstellar matter just above the progenitor. Of course, next question is how common this kind of dense circumstellar matter are around in these ordinary type 2 supernovae. So I just show one example which happened to be observed just after the explosion, and that told us there should be some dense circumstellar matter. But how common is this? So to answer this question, we made a lot of model to having different mass loss rate, different beta, and different progenitor, and so on, and modeled a lot of light curve and how these different parameters will change the light curve. So this is mass loss rate. When we change the mass loss rate, so we start from 10 to the minus 8 solar mass per year to 10 to the minus 2 solar mass per year. And this is in R band, and this is in G band. And of course, as the mass loss rate increases, that directly change the amount of circumstellar matter. So as the circumstellar matter increases, you have much brighter light curve from this circumstellar matter interaction. And then we can also change beta, and this is the bottom. The lowest model is beta 1, and the highest model is beta 5. It doesn't affect very much the light curve. So other parameters are fixed, but if the beta increases, then that makes the density higher for near the progenitor, as if we assume the same parameter. So that makes the light curve slightly brighter than larger beta makes the light curve brighter. So we made many different kinds of models, and of course we need observation to compare. And fortunately, there was a survey to find supernovae just after the explosion using DECAM. So this DECAM is a big telescope, like 4-meter telescope located in Chile, and it has a very huge CCD camera. And they did supernova survey to discover supernovae just after the explosion. And what they found is that they basically found a lot of supernovae, and they found 26 type 2 supernovae just after the explosion. So these are all type 2 supernova light curves. 26 type 2 supernova light curves they found. And as you can see, all of them have the information on the rise time. And we don't have spectra at the beginning, but we basically fitted our model with circumstellar matter to see how much circumstellar matter is required to explain this early light curve. And green is in G band, and some cases you also see the red, and that's R band. So we have sometimes different bands. And so these dashed light curve is the model without circumstellar matter. So when there's no circumstellar matter, then as I explained, the rise time is too long to explain this rise of the type 2 supernova in general. And these lines are basically light curve model with circumstellar matter. And the different lines show different parameters. And but basically, when we have a dense circumstantial matter, you can better explain this rapid rise. But we also found some exception. These two are kind of exception, and you don't need to. So dashed line and the best fitted light curve doesn't have much difference. So these two didn't need to have dense circumstantial matter just above the progenitor. But otherwise, this dashed light curve, which doesn't have any circumstantial matter, couldn't explain this rapid rise.
Excuse me.
Yes.
Angular cover of distance.
Could you say it again?
8 degrees.
Sorry?
What is the angular cover of this?
So this model is spherically symmetric. Assumption is spherical symmetry. So 100% covered. So that's another question, of course. And yeah, that was 26 supernovae found during the survey, but of course we can try to fit some type 2 light curves discovered in different surveys just after the explosion. And this is one light curve discovered from the Kepler satellite. So it had detected, this catched this supernova, type 2 supernova, just when it's exploding. And this line actually our model explains very well. And yeah, we basically this circumstantial matter is required to explain these early quick rise of type 2 supernovae. And based on our light curve fitting, we could get the required massless rate of the progenitors, and also this wind acceleration parameter beta. From the light curve fitting, as you can see, this acceleration parameter is not well constrained, but it's around, the center is around 3-ish. And but what we can clearly say is that the mass loss rate of the progenitor shortly before the explosion of these red supergiants should be higher than 10 to the minus 3 solar mass per year, or around there. And there is some exception, but mostly the mass loss rate should be very high. So this is another way of seeing the same result. So this is probability distribution function. And please see the black line, which is corrected for some bias. And so we see that mostly the mass loss rate of red supergiant just before the explosion should be more than 10 to the minus 4 solar mass per year. And as I showed at the first slides, and this is mass loss rate of the again the same kind of similar figure to what I showed before, and red supergiant mass loss rates up to minus 4 solar mass per year or so. This is in the range of the supernova progenitor luminosity. But what we found is the red supergiant, those explode. So this is not exploding. This is long before the explosion. But those exploding red supergiants just before the explosion should be exceeding this mass loss rate much higher than the mass loss rate. So somehow these progenitors should be supernova progenitors just before the explosion is losing a lot of mass just before the explosion. And what's the difference between type 2n supernovae and these ordinary type 2 supernovae? So as we saw, type 2n supernovae continue to show these narrow lines and continue to be bright for a very long time. And so that means, so this is again the density structure. This is radius and density. And for the type 2n supernovae, we saw like 10 to the minus 3 solar mass per year or even more. But let's say this is the this is typical density structure, and this was this should be this structure should be extended for a larger radius to have a continuous interaction. So this mass loss enhancement of the progenitor before the explosion should be lasting for more than 100 years to have this extended structure. So this high mass loss rate should be continued for a long time. But in the case of ordinary type 2 supernovae, so this type 2 supernovae will eventually become just normal type 2 supernova. So that means this high density structure should be just above the progenitor. So it shouldn't to be extended, because if they are extended, these supernova will become type 2n supernovae. So this high density structure just sits just above the progenitor, and then the mass loss rate, the density should be very low after some density, some radius. So that means in the case of ordinary type 2 supernovae, the mass loss rate should be enhanced before the explosion to explain this rapid rise and the narrow lines we see at the time of just after the explosion. But this high density shouldn't extend for long, and this should go to the normal regime of mass loss rate. And that means this mass loss enhancement should be happening not within 100 years before the explosion, around 100 years before the explosion, but not much longer. So the conclusion is that probably this mass loss enhancement in type 2 supernova progenitors are happening in general, even in the ordinary type 2 supernovae, that we can tell from the rapid rise in the type 2 supernova we observe. But in the ordinary type 2 supernova progenitors, this mass loss enhancement is somehow not lasting for a long time. It just happens within 100 years or several decades before the explosion. But in some cases, for the progenitors we observe as type 2n supernovae, this mass loss rate enhancement is somehow lasting for much longer time, and that's why we observe them as type 2n supernovae instead of ordinary type 2 supernovae. So also I don't remember if we covered shock breakout, but if there's so one prediction from the ordinary type 2 supernova light curve theory is when the shock, so at first shock is when at the time of the supernova explosion, shock wave emerged at the central part of the star, and then this shock wave just continued to propagate, and when this shock reached the surface of the star, then we start to see the light from this explosion suddenly. So what is predicted is there's some signal called shock breakout, which just illuminates. So it's just after the when the shock wave reached the surface of this star, we expect to see some brightening for short time scale, and then it gets bright. But if there's a dense circumstantial matter surrounding this progenitor in general, then this shock breakout signal may be smeared in this dense circumstantial matter, and probably this short time scale shock breakout may not be observed, and maybe we see some effect from the shock, the dense interaction between the supernova ejector and dense circumstantial matter more dominantly. But yeah, this is one possibility. So I have talked about the hydrogen-rich supernova, so type 2 supernova. So type 2, yes?
Yes. Before we go further away, I wonder, so your point is that
I'm wondering about the following point. You said that the Maxwell's rate is a prerequisite feature, right, to explain like curves of type 2n and type 2 with rapid rise time, and the difference between them appears to be in the duration of the phase before the core collapse.
Yes.
And as we heard in the previous days, and we understand that the core collapse starts after the silicon burning and all these stages, late stages of evolution. And assuming that we have just similar masses for progenitors in both cases, for type 2n and for these guys, we would we are left with the situation when we just have some final stage of core evolution, which accompanied by increase in the mass loss, right?
Yes.
And because you use the radiation with acceleration formula, definitely it relates to the acceleration by radiation, right? So it's increasing the luminosity in the final cry, so to say, the start before the collapse, increase in the luminosity, which produces this huge mass loss. Right?
Yes.
So what is so in for me it's not strange that because the core evolves by itself without having any dynamic connection with the envelope. So we have we have arbitrarily have a time of course.
So that's the big question.
At any time, right? And in this case, we would expect some distribution, or not a distribution, but some fraction between our ratio, number ratio between type 2n and type 2 with rapid rises.
Yeah.
And my question is, if these considerations have something to do with reality, then how this existing statistics could it confirm? Can it confirm these considerations, or just it's not consistent with it?
So it's hard to. I will come back to this point, but it's very hard to connect in the standard picture the evolution of core to the stellar surface, the mass loss. So that's happening very different radius, and so there's several suggested ways to make this connected, but we are not exactly how, and we don't know. And yeah, as you said, the fraction of type 2n supernovae and ordinary type 2 supernova may tell you something about that, but we actually know in type 2n supernovae have very diversity in their progenitor. So they not may be always coming from, so for the ordinary type 2 supernovae, they are from red supergiants. But we know in some cases type 2n supernovae are happening in a very massive end of the like luminous blue variables. And some of them may be from the red supergiant, or some maybe none of them may be from the red supergiant. We don't know. Probably some of them may be red supergiant, but so we don't know exact fraction of in the ordinary red supergiant explosion. In what fraction goes to type 2n and what fraction goes to normal type 2 supernova. We don't know this fraction, so it's hard to make some argument based on this fraction.
Okay.
But the time scale is quite a difficult issue, and we don't know exactly how these core evolution and surface evolution is connected. So this was about hydrogen-rich supernovae, and you may wonder if this kind of stuff can happen in hydrogen-free supernovae. And the answer is yes, and we now start to see some narrow helium emission in some cases in type 1b supernova, and we now have some type supernovae called type 1bn supernovae, and these. So these example of type 1bn supernovae. And what is amazing about these supernovae, these are kind of bright supernovae, and these lines hard to see, but these are like stripped envelope supernova light curve. And this is scaled in the peak luminosity, and these lines are like supernova powered by nickel decay. But what we see in type 1bn supernovae is that it rises quickly and decays extremely rapidly. And if they are powered by the nickel decay, then this light curve should eventually go this cobalt decay line. But most of them doesn't go, and it just decays. So they are bright, but they must be this luminosity cannot be explained by the nuclear decay as in the standard type 1bc supernovae. But this should have another heating source, and from the spectra, we think these are powered by the circumstellar matter interaction. And the mass loss rate from these type 1bn supernovae are estimated to be, let's say, around 10 to the minus 2 solons per year or something like that. So this projector doesn't have much hydrogen, but still they can have similarly high mass loss rate shortly before the explosion. And what's interesting is that in one case, this projector of this is one type 1bn supernova, and this projector was observed to got bright 2 years before the explosion. So let's see. So this supernova was exploded here, like in 2006, and it's called 2006 JC, and it became bright and faint. But one person had observed this galaxy, and that person found like in 2 years before this supernova explosion, at the same location, something was getting bright. So this supernova projector was somehow got bright 2 years before the explosion, and then 2 years later, it exploded. And this was type 1bn supernova, and there should have been dense circumstellar matter surrounding this projector. So probably at this moment, 2 years before the explosion, some eruptive event from the surface of the star, this projector happened, and that made some dense circumstellar matter. And then the actual supernova explosion happened 2 years later, and this exploded ejector supernova crashed into a circumstellar matter, which was probably made 2 years before the explosion. So this kind of phenomena is also seen in Wolf-Rayet stars. And then that was type 1b supernova, so they didn't have any, didn't have much hydrogen, but there was helium. And then there's a similar case even in type 1c or broadline type 1c. These supernova are sometimes associated with gamma ray bursts. And this supernova was observed, the same field was observed many times even before the explosion. So this supernova type broadline type 1c, which has a lot of kinetic energy and the broad line component, and this was exploded at some time, but they found this supernova was kind of bright even before this actual rise. So you had some luminosity increase from, let's say, 8 days before the explosion. And then there's some short brightening was reported. They also found some short brightening 15 days before the explosion, and then it exploded. This had some signature of the circumstellar matter interaction again just after the explosion. So they probably these kind of progenitor was doing something to make some dense circumstellar matter surrounding this progenitor, which doesn't have any hydrogen or even helium, and then this supernova was crushed into this circumstellar matter created just before, like several tens of days before the explosion. So finally, this was already asked by the Konstantin, but so I was talking about I was suggesting or saying that these mass loss rates, some increase in mass loss rate somehow should be connected to the supernova explosion. But in the standard evolution theory, that's very hard because that's not natural because so the collapse of the star is happening at the center of this star, and the red supergiant has huge radius. So this difference in radius, I mean, this mass loss is happening at the surface of the star, and the explosion of the supernova are triggered at the center, and it's extremely in an extremely different radius, and it's not usually connected to each other. And connecting the explosion and mass loss is extremely difficult question, and we don't know exactly how this is happening. And this is the final. So this is Kippenhahn diagram, and final one example of the evolution of the 15 solar mass progenitor. And this is time to the collapse, and in the end, silicon burning happens like several days before the explosion, and oxygen burning occurs like from about 1 year before the collapse, and neon burning happens there. And I was saying like there should be some mass loss enhancement before or longer than 100 years before the explosion. And 100 years, there's not much new thing happening. And the carbon burning is happening there. So some mass loss, so this after some carbon burning or shell carbon burning, somehow this mass loss needs to be kicked off, and then continue until the time of the explosion. And in the case of ordinary type 2 supernovae, the mass loss increase should be starting within like 100 years before the explosion. And in that case, not much thing. I mean, there's shell burning, but it's nothing very peculiar. Especially is happening at the center. But somehow, this evolution at the center is affecting the surface evolution. And as we said, as I showed before, some cases in the 2 years before the explosion, this mass loss, some brightening was found, and that probably corresponds to central neon ignition and so on. But yeah, but again, this is happening at the center, and how this will affect the surface mass loss is another question. So the big issue is, so if we see the dynamical time scale, of course, in the 10 solar mass star with 100 radius, I mean, you can do dynamical, if you can make dynamical, if you can somehow connect dynamically this center and the surface, you can still do this. And the thermal time scale is longer, and the nuclear time scale, of course, is much longer. So it's connecting, so we need somehow this, so you cannot make this connection in a thermal time scale, so it's not thermal, something thermal is happening here, but some more dynamic processes needs to happen to make this connection between the center of the collapse of the star and the surface mass loss. And there's, of course, some suggested way. This at the center, there will be huge convective activities that may cause some acoustic wave inside, and this acoustic wave this acoustic energy may be dumped somehow into this this at the surface, and that may be able to push the surface of the star, and that may lead to some high mass loss rate just before the explosions. But that's one idea, and but we don't exactly sure if this is really happening in the star, and if this can explain the time scale properly and so on. The many issues are still remaining, but what we know now is definitely in many cases somehow central evolution of the stars are somehow connected to the surface evolution, the surface mass loss of the supernova just before the explosion. So basically that was it, and I have introduced the circumstellar matter property of the supernova progenitors, and the very clear case we see the interaction is type 2n supernova, and to have long-lasting interaction signatures in this type 2n supernova, the mass loss should be increased for more than 100 years before the explosion to see this to see the continuous mass loss. But the mass loss rate needs to be more than 10 to the minus 3 solar mass per year, and that is not observed in normal stars. And the other type 2 supernovae, ordinary supernovae, they are still somehow seems to have dense circumstellar matter, but they should be, this dense circumstellar matter, it just locates just above the progenitor. So the mass loss enhancement should be much shorter, in much shorter time scale. And yeah, how to connect this explosion and mass loss is not yet clear. And we saw these type 2 supernovae maybe generally having high mass loss rate, type 2n of course, and I show one example of 1bc broadline, and some 1b type 1b supernovae also have mass loss enhancement as we see in type 1bn. So in that sense, like most large fraction, or maybe 75% or so of these stars, or even more, may be losing a lot of mass just before the explosion, and somehow the central evolution is connected to the surface mass loss. That's it. Thank you very much.
Thank you very much for exciting presentation. So, any questions, please? Masaru-san.
Yeah, 10 to minus 3 from ISP, but you also mentioned that Takashi is doing something like that. So
Yes.
what's the mechanism of the
We don't know. But in the case of Eta Carina, one suggested scenario is, it's in binary system, and it's in eccentric binary system. So it also depends on to whom you ask, but that mass loss maybe that Eta Carina may have been like 3-body system, and then it may be merged, and that may cause this eruptive event. But some people suggest this eruptive mass loss from Eta Carina is continuing several times. If it's continuing several times, of course, that's not one-time event, so there should be some other way. But we know there's this eccentric binary system is Eta Carina. So this binary evolution itself may be somehow connected to this large mass loss. But we don't know exactly sure how this mass loss have happened.
So in this sense, binarity may be important. So that's one case, but the other case we have large mass loss rate even there's no companion star. So like 10 to the minus 3 can be reached in, so 10 to the minus 3 or up to around this mass loss rate, you can in principle reach by the line driven 10 to the minus 3, and then you can enter the continuum driven regime that can lead you up to like 0.1 solar mass per year. But of course you need to catch all the photons and continue to push the material, but in principle you can go up to 0.1 solar mass per year also. Above that, radiation cannot do. It's hard. So once or once per year, there should be something else.
Okay. Other questions? Just a small comment about this time scale. These time scales, if you show them again, this one, yes, all of them seem inappropriate, but say geometrical mean between the first two with the right estimate. For example, look at the sun. The convection overturn in the sun, it's not a dynamical time. It's not 1 hour, right? It is it's months or years for convectional return in the sun. It depends on the length.
Yes, definitely, yes.
Etc. Convection is something very thin. It's not well understood at all. And here again, we also have a situation with massive convective shells, which somehow enrich the energy from inside the star.
Yeah.
So I suspect this could have. Of course, it is difficult to connect. I agree with you because we do not understand the convection of these principles. But it seems to be that something like convective time could play the role.
Yeah, maybe yes.
In this story.
Yeah.
And also, for instance, in HEB stars, in mirror-like variables, we have these slow pulsations.
Yeah.
We know the reason for these pulsations because of the thermal instability near the degenerate core. Maybe something similar would take place in this.
Yeah, but it needs to be connected to the collapse and so long-term muscles may be explained in that way. It's possible. Yeah.
Okay. Okay. Thank you very much again.